And next topic is quantum mechanics. And the first part of this quantum mechanics is the inadequacy of classical mechanics. And the major inadequacies of classical mechanics are the classical mechanics does not hold in the region of atomic dimension. It cannot explain the motion of atoms and atomic particles. And the second one is the classical mechanics cannot explain the stability of atoms. And the third one is it failed to explain the spectrum of blackbody radiation. The fourth one is the classical mechanics could not explain the observed variation of specific heat of solids. And the fifth one is classical mechanics could not explain the origin of discrete spectral lines of atoms. And the last one is the classical mechanics failed to explain the phenomena like photoelectric effect, Compton effect, Raman effect, etc. And we will study these inadequacies in detail. The first one is the classical mechanics explain the motion of celestial bodies like planets, stars, and all microscopic bodies as well as microscopic terrestrial bodies which are moving with speed very much less than the speed of light in vacuum. The classical mechanics is based on Newton's laws of motion and it is also called Newtonian mechanics. And the classical mechanics explain the motion of objects which are directly observable or observable with the help of microscope. That is, it cannot explain the motion of atoms or the atomic particles like electrons, protons, and neutrons. And the second failure is that the classical mechanics could not explain the stability of the atom. Consider the picture of an atom. In an atom, there is a central positively charged region called the nucleus, and the electron they are revolving around the nucleus in an orbit. And according to the classical theory, an accelerated charged particle should continuously emit electromagnetic radiation. Electron is a charged particle and this electron is an accelerating one, and hence during the orbiting of the electron around the nucleus, this electron should continuously emit electromagnetic radiation, and therefore the velocity of the electron should decreases continuously. And finally, the electron which comes closer and closer to the nucleus, and finally it collapses with the nucleus. That is, the electron which loses the energy finally spirals into the nucleus, and because of this the atom will be unstable. That is, when an electron or a particle it collides with the nucleus, some type of particles will be emitted from the nucleus, and because of this process the nucleus becomes unstable or the atoms becomes unstable, and that is the classical theory could not explain this phenomena. But according to the quantum theory, an accelerated charged particle should emit energy discretely. And the third one is it failed to explain the spectrum of blackbody radiation. And a blackbody is one which absorbs all the radiation incident on it, and it emits all those radiation when the body is heated. And it is a good source of thermal radiation, and this blackbody neither reflects nor transmits any of these radiations. A perfect blackbody emits radiations of all wavelengths in a particular region of the electromagnetic spectrum. So it gives a continuous spectrum. Here in the figure, we can see that the emissive power or the intensity of radiation, it is plotted against the wavelength lambda. And here in the spectrum, we can see that the energy of a blackbody radiation is not shared evenly by all wavelengths. And the spectrum of blackbody radiation shows that some wavelength gets more energy than the others. That is, at a given temperature, the intensity of the radiation it increases with the wavelength and it reaches a maximum value and then it decreases. And the wavelength at which the intensity of radiation becomes maximum is called lambda m. That is, lambda m is the wavelength at which the intensity of radiation becomes maximum. And from the figure we can see that as the temperature increases, the intensity of the radiation also increases. And also with the increase in the temperature, the lambda m, it decreases. That is, this lambda m, it is shift towards the lower wavelength region. And Bean was the first physicist who studied the distribution of energy in the spectrum of blackbody. And this Wien's formula, it was found to agree with the experimental curve for shorter wavelength region only. And later, Lord Rayleigh and James Jeans, they tried to explain the blackbody radiation spectrum based on a formula. But this formula is also found agree with the experimental curve only for the longer wavelength region. And none of these formula could explain the entire shape of the blackbody radiation spectrum. And later, Max Planck in 1901 came up with a solution. And Planck explained the blackbody radiation spectrum, the entire spectrum, based on his quantum theory. And the next failure is that it could not explain the observed variation of a specific heat of solids. And we know that the molar specific heat of a solid at a constant volume, that is Cv, it can be defined as the amount of energy that must be added to a 1 kilogram mole of a solid whose volume is held fixed to rise its temperature by 1 Kelvin. And in a solid, the internal energy arises due to the vibration of its constituent atoms. That is, in a solid, the atoms can vibrate along the three perpendicular axes. So each atom may be thought of as a three-dimensional harmonic oscillator. And its mean thermal energy can be represented as E is equal to 3 kT. And if N is the number of atoms in the solid, then the energy can be represented as 3 nkt. Or this Nk can be represented as R, that is, it can be represented as 3RT. Therefore, the specific heat at constant volume can be represented as Cv is equal to dou E by dou T at constant volume. And this will give the value of specific heat as 3R. And this is called the Dulong and Petit law. And the first classical attempt to study the heat capacities of solid was made by Dulong and Petit, and they showed that the molar specific heat of solids at a constant volume for all the material is a constant and is equal to 3R, where R is the universal gas constant. But when the temperature is lowered sufficiently, the specific heat, it decreases and it approaches 0 as the temperature approaches 0 Kelvin. Thus, the classical idea failed to explain the variation of specific heat of solids with temperature. Later, the Einstein explained the anomaly in the specific heat of solids using quantum ideas. And then after Einstein, then Debye improved the Einstein's model and then explained the specific heat of solids. Thus, the classical mechanics, it failed to explain the observed variation of specific heat of solids. The classical mechanics could not explain the origin of discrete spectral lines of atoms. In the figure, you can see the discrete and continuous spectra. And the next failure is that classical mechanics fail to explain the phenomena like photoelectric effect. And we know What is a photoelectric effect? When light is incident on a metallic surface, then electrons, they are released from the metal, and these electrons are called photoelectrons, and the phenomenon is called photoelectric effect. And when light falls on a metal surface, the emission of electron depends on the frequency of the incident light. That is, there is a minimum frequency of light which is required for the emission of electrons from a metal surface, and this frequency is called the threshold frequency. And this threshold frequency, it varies from metal to metal. Here in the figure we can see that when an intense red light it falls on the metal surface, no electrons are emitted. But when a feeble blue light it is incident on a metal surface, then electrons are emitted. Here we can see that the red light have a high wavelength and the blue light have lower wavelength. And we know the relation, the frequency is equal to the velocity by wavelength. For the red light, lambda will be greater and hence the frequency will be lesser. And here in this case, when an intense red light falls on the metal surface, then it could not produce any electron from the metal because the wavelength for the red light is very high but its frequency is very low. And for the electrons to emit from the metal surface, it should have a minimum frequency, and this frequency is called the threshold frequency. But for the blue light, its frequency is very high because the wavelength is very less. Because of this high frequency, it can emit electron from the metal surface. That is, the energy of the photoelectrons does not depend on the intensity of the incident light, but it depends on the frequency of the incident light. And the classical mechanics could not explain all of these characteristics, and hence the credit for solving this problem goes to the Albert Einstein. Albert Einstein in 1905 succeeded in explaining the photoelectric effect on the basis of the quantum concept. And these are the limitations or inadequacies of classical mechanics. And later quantum mechanics explained all these inadequacies, or it was the origin of the quantum mechanics.